Hi, I'm Min-Chi Zhang from Purdue University. Today, I will present our work on characterizing massively parallel polymorphism. GPU programmability has improved with each new generation. At its inception in 2006, CUDA began by supporting a subset of C programming language. In the years and CUDA versions that followed, C++ language concepts such as inheritance, dynamic memory allocation, and polymorphism began to be supported. Since CUDA 6, a unified virtual memory space between the CPU and GPU has been supported. The shared memory space greatly simplifies the GPU porting process and enables the CPU and GPU to share more sophisticated data structure without structuring the code. Finally, in the latest version of the CUDA, much of the C++ standard library is now supported on GPUs. This increased programmability allows programmers to easily port multi-threaded CPU code to the GPU, with minimal changes to the code and no changes to the underlying data structure. To illustrate the ease of porting a polymorphic multi-threaded CPU program to the GPU, consider the PageRank implementation from the object-oriented graph tree application, whose CPU code is shown here. The original polymorphic CPU implementation has multiple virtual functions that hide the implementation details of the graph's data structure. Porting the code can now be a simple process with very limited modifications, potentially done by an automated tool. Specifically, a global keyword is added. A linear thread ID is computed. And all the virtual functions, data structures, definitions, etc., can remain completely unchanged. Support for those productive programming features clearly makes the programmer's job much easier and allows them to more easily experiment with different code on the GPU with little initial cost. However, the efficiency of polymorphic code executing on the GPU has not been well explored. Our paper performs the first detailed characterization of this massively parallel polymorphism. We examine how efficient such code is, explore the space where the overhead can be mitigated, and suggest open areas of future research. To understand the implementation of runtime polymorphism in contemporary CUDA, we begin by reviewing the implementation of runtime polymorphism on CPUs. In this example, we assume a two-core CPU accessing two objects of different types. To call virtual functions on the CPU, each core accesses each virtual table pointer embedded inside each object. The vtable pointer is then dereferenced, and the appropriate virtual function address is loaded, and an indirect jump instruction calls to the corresponding function. CPU virtual functions add additional latency to the call and require more sophisticated branch prediction to avoid costly losses to the instruction level parallelism. From a detailed reverse engineering the implementation of virtual functions in CUDA, we have discovered that the implementation of virtual functions in contemporary CUDA is extremely similar to the classic implementation in CPUs, but executed on a dramatically different architecture. On GPUs, each core supports many more threads which are organized into verbs, where parallel threads are executed in lockstep. The syncing length for one verb can access up to 32 objects on an NVIDIA GPU if each thread is accessing a different object. On each core, there are typically dozens of verbs present, resulting in many thousands of discrete objects being accessed by the core in a quick succession. In this example, each thread accessing a different object instance for only two object types, and this is very typical. Programmers usually only define a limited number of concurrent classes, but can create thousands of objects instances for those few types. Intuitively, accessing all these functions in quick succession can cause a significant amount of memory pressure in a relatively short amount of time. In our paper, we expand beyond this simple intuition by studying the effect of runtime polymorphism in isolation using Microbenchmark. This expands to introduce Parapoly, the first benchmark suite featuring polymorphic GPU applications. In our Microbenchmark, we quantify the overhead of virtual function use as a function of both the control flow divergence in the application and the compute density of the virtual function. Then, using Parapoly, our diverse set of polymorphic application whose GPU implementation mirrors a corresponding CPU implementation, we examine and isolate the effects of virtual function, both in terms of direct overhead and indirect overhead caused by missed compilation time optimizations. To cleanly separate the cost of calling virtual functions in a controlled environment, we create two microbenchmarks where the control flow divergence and the compute intensity can be varied. In one, a virtual function call is used to arbitrate control flow, and in the other, a switch statement arbitrary control flow between different direct function calls. Both microbenchmarks perform the same compilation computation in the function call that can be varied. In the virtual function-based benchmark as pictured here, each lane of the verbs access different objects, where the types of those objects can be varied. In this example, we are showing the case where there's no control flow divergence because each lane is accessing an object of the same type, hence calling the same virtual function. For simplicity, we show a verb with only 8 threads here. Verbs in the NVIDIA machines we study have 32 threads. To isolate the performance overhead of using virtual functions, we normalize the execution time of the previous virtual function case to the same microbenchmark without any virtual functions. The function is directly called. Both microbenchmarks can be modified to increase the level of control flow divergence in a verb. In this example, divergence is increased to 8 ways, where there are 8 different types accessed by the same verb. Hence, different virtual functions are called. And the previous 8-way diverged virtual function microbenchmark is compared to an 8-way diverged microbenchmark that use a switch statement to arbitrate the same control flow pattern to directly call the corresponding function. In this plot, we show the overhead of calling a virtual function with no divergence versus the same virtual function, implemented as a direct function call at different computing densities. When this computing density of the function is low, the overhead of using virtual functions instead of normal function is about 7x. As the computing density of the function increases, the relative overhead of using virtual functions calls and eventually disappears. If the work done in the function dominates the time to reach the function body, which it does not have a very high computing density, then the cost of calling a non-diverged virtual function is minimal. In contrast to the non-divergence case, the fully, which is 32-way divergence case, shows minimal overhead. Independent of the computing density, when the code call is highly diverged, the time spent inside the function body increases by a factor of 32, as all 32 passes are serialized in both the V function and no function case, and this relative overhead of reaching the virtual function is minimized. At other intermediate levels of divergence, the trends are similar with overhead being roughly between the no divergence and fully divergence case. The two key takeaways from our microbenchmark study are, at a high computing density, virtual function overhead is mitigated, and that calling virtual functions is much more costly in high converged code. To complement our microbenchmark, we create Parapoly, an open source GPU benchmark suite that focuses on runtime polymorphism. The application in Parapoly comes from two primary sources. Existing GPU applications from an object benchmark suite called Dinosaur, which were devirtualized by the original authors to study memory allocation behavior on GPUs. We revirtualized the benchmarks in Dinosaur to mirror polymorphic CPU implementations of the simulation algorithm it contains. The second source of applications come from CPU implementations of the object-oriented workloads, graph tree, and paramorphic ray tracer. In all, Parapoly represents a set of GPU benchmarks where programmability and maintainability with CPU implementation is a first-order concern. The first characteristic we study is the breakdown between object initialization and the application's computation. We split the execution of Parapoly workloads into two phases, initialization phases and computation phases. The initialization phases represents the GPU kernel time to allocate and construct the objects. Parapoly workloads will allocate from 1,000 objects to several tens to the 6 objects as shown in the plot on the right. The computation phases represents the time for the GPU computation kernel. Usually, the initialization phases happens once, and computation phases may recur. We display the breakdown of two phases execution time on the left part. The two phases vary differently for different workloads. Some workloads cost more than 90% of the time on the initialization phases, while the other cases less than 30% on these phases. This plot indicates that the memory allocator on the GPU is not efficient for a large number of objects. Recent top conference papers also notice the same trend. To further explore the virtual function overhead in Parapoly benchmark suite, we also refactor the workloads with the other two limited study versions, except for the virtual function version. VF represents the versions that use virtual functions. Calling targets are not known until runtime. NoVF assumes that you know the targets at compilation time, so you can directly call the targets. This version indicates the limit study that you can devirtualize the virtual functions of the application. Inline assumes the further optimization that you can inline the devirtualized functions. We compare the execution time for VF, NoVF, and inline, and normalize the performance to the inline, which is the most optimized one in the plot at bottom. The normalized execution time reduced 65% from VF to NoVF. To understand why this improvement happens with NoVF, we provide in detail into the memory access instructions. We first notice that the global loads decrease around 49%. This is because NoVF does not need to retrieve numerous virtual table pointers and relatively few virtual function pointers comparing to VF version. Moreover, we discovered that the local loads and stores are also reduced about 66%, since NoVF also enables the compilation opportunity that registers inside the original virtual functions don't need to spill out to the local memory. From the profiling details, we can conclude that this great improvement from VF to NoVF comes from the mitigation in memory contention. Then let's talk about the performance difference between NoVF and inline version. From NoVF version to inline version, the performance improves 12%, which is less from VF to NoVF. We explored the reasons for these differences and then found out that the compute and control instruction decreases 58 and 67 respectively. This is because both the preparation instruction for calling functions and calling functions are saved in inline version. To draw a conclusion, we discovered that GPU polymorphism bottlenecks are different from CPU polymorphism. Microbenchmark experiment shows 7 to negligible overhead according to different control flow divergence and compute density. Parapoly benchmark suite shows a geometric meaning of 77% overhead in real scenario. Comparing the VF to the NoVF version, the cause of the great overhead is a virtual table and virtual function operations that introduce memory contention and masked compilation optimization. Comparing the NoVF to the inline version, which has less effect, the root costs are the function call and the function setup cost. According to our experiment, we propose two alternatives to support efficient polymorphism on GPUs. First, we need to rethink the virtual function implementation on GPUs. Should we follow the similar way to support GPU virtual functions as CPU, or we should reconsider implementing the virtual function with respect to the GPU architecture? I think the answer is the latter one. Secondly, there's an indication from the versions of Parapoly site to show the new compilation opportunities for just-in-time to devirtualize and inline virtual functions on GPUs. If you are interested, please read our papers and download our Parapoly benchmark. Thank you.